Welcome to the Nanovation Podcast. Information about this and other episodes can be found at fillerlab.com/nanovation. If you like what you hear, be sure to tell a friend or leave a review at Apple Podcasts. It really does help. I welcome your thoughts and suggestions. You can contact me on Twitter at Michael Filler or via email at nanovationpodcast@gmail.com. Thank you to the Chi Foundation for their generous financial support.
I believe there's a spectacular opportunity to develop a technology that I'm calling Digital Atomic Scale Fabrication to provide the much better nanoscale manufacturing precision required to fulfill this promise of nanotechnology. And this, I believe, will enable very complex, extremely reliable, and really spectacular performance products that are not restricted to electronics.
That's John Randall from Zyvex Labs. He joined the podcast to discuss his far-reaching vision for nanotechnology and nanomanufacturing. We discuss what he calls digital atomic scale fabrication, the future products it might enable, the critical need for error correction, and why today's semiconductor manufacturers are unlikely to lead the way. John also shares a number of captivating stories from his career. If this episode doesn't get you excited about the promise of nanotechnology, I don't know what will. This is the Nanovation Podcast, an exploration of big innovations emerging from small things. I'm Mike Filler, your host and a professor at the Georgia Institute of Technology. Enjoy the show. It's my pleasure to introduce John Randall, the president of Zyvex Labs. And he's a pioneer in digital atomic scale fabrication. Sometimes that's called atomically precise manufacturing. And we'll get to that soon. There's lots to talk about. But I was hoping you could start by talking about where you got your start. Who were your role models and how you got to where you are today?
Thanks so much for that question. First of all, let me say my entire career has been as a micro or a nanofabricator, which I tell people might mean that I tell small lies. No, really, I work with FIBs, focused ion beam instruments. So that's a nano joke. But the way I ended up being a nanofabricator is, if I back way up, my misspent youth was spent in Houston, Texas, that we were talking about a short while ago. My father was a PhD chemical engineering Longhorn who worked in natural gas processing. And after working for a number of other firms, he founded a company, the Randall Corporation, that literally revolutionized the way natural gas processing plants were built and the way they operated. And he was in the right place at the right time with a great idea, was very successful in doing that. So I had a role model, but I was frankly more interested in electronics than in natural gas processing plants. And so I became a professional electrical engineering student at the University of Houston. And I might have gone elsewhere for grad school, but starting when I was an undergrad, I got to run the only publicly available scanning electron microscope in the entire metroplex of Houston. So that was a great education that lasted all through a graduate school.
I'm sorry, can I ask you what year that was?
74, I think ABL Carey, the professor that hired me to do that, got an NSF grant, I believe was 74.
It's funny because I think a lot of students today think of SEMs like toasters.
Yeah, they're everywhere. So it was the only publicly available one. So I not only got to support virtually a huge number of departments around campus: physics, chemistry, biology, geology, electrical engineering, mechanical engineering, chemical engineering, also. Failure analysis firms around the city of Houston came in to use it, including also the Houston Police Forensics Lab came in to use it. I'll tell you a trivia joke here, or a little bit interesting bit of trivia in a second that again will date me. But also NOAA, we did the first SEM exploration or imaging of brine shrimp larvae, and NASA. I got to look at moon dust.
Ooh. So what's
Really?
it look like?
It mainly spherical, because a lot of there's a lot of spherical particles that come from meteorite impacts that the molten stuff flying away in the vacuum forms beautiful little spheres.
I would not have thought that, but okay, it makes sense.
I wouldn't have thought it either, but that's the way it works out. So back to my trivia point. While working for the Houston Police Forensics Lab, there's a very distinct topography to cannabis leaves. And so they would bring in these minute little bits of cannabis leaves, and we'd identify them in the scanning electron microscope. So I bring that up because I can recognize, after we looked at enough of these things. And so do you remember the original Blade Runner, where Harrison Ford is out in search of a woman who is an android who has an android snake? And did you see the movie?
At some point, although my wife will tell you that I'm horrendous with pop culture like this.
Okay, well, so I can you don't have to remember it. Harrison Ford finds this snake's skin scale where the android that he was looking for was at one point in time, and takes it to a street SEM vendor in the dystopian universe of LA, and has him look at what, for somebody that hadn't looked at scales or microscopic things before, it looks perfectly like it might be the surface of a snake scale that he read a little serial number off of that identified where it was made. But in fact, what he was looking at was the very distinctive topography of a cannabis leaf.
I didn't realize that was in the movie, but it's kind of it's a little prescient, actually.
Yeah, it's entertaining. Well, but so I have digressed. So when I eventually ran out of, so I got interested in small things. I modified the SEM to do E-beam lithography, built my own X-ray lithography system, and started out my career as a nanofabrication nerd. When I ran out of double E degrees to get, I was forced to get a real job. I went to work at MIT's Lincoln Laboratory, and I really worked more on ion beam lithography, which was entertaining. Not the focus type, ion beam printing through a stencil mask. But after 4 Boston winters, and at this point in time I should point out that I'm in a mixed marriage, you need to understand. You see, I'm an electrical engineer, and my wife's a chemical engineer.
Well, what's wrong with that?
Nothing, except that we had some really interesting arguments. When you say, for instance, when you say efficiency, it means one thing to an electrical engineer and something entirely different to a chemical engineer. And my extremely intelligent analytical wife was making these unbelievably stupid statements, I thought, because we were both talking about efficiencies, but in very different ways.
I have that problem with the word throughput these days when I talk to people in electrical engineering. I say throughput from a manufacturing perspective, and they're thinking something about device physics.
Yep. That's a word that often gets misconstrued depending on the context. But at any rate, my wife, after 4 Boston winters, got hold of me and said, "Son, get me the hell out of here and back to Texas." So in '85, we moved to Dallas. I went to work at Texas Instruments. I worked in Central Research Laboratories for 10 years, mainly on quantum resonant tunneling devices, with an unbelievably talented group of engineers and scientists. But in spite of that cool gig, in 1996, I moved over to the Silicon Technology Development Group, narrowly missing being sold to Raytheon by just happenstance. But I took the assignment so I could work in Belgium for a couple of years at IMEC. And if you like beer and chocolate, Belgium is just heaven. So I worked there, did some great work on mainstream deep UV lithography, and acquired a taste for Belgian beer and chocolate. Came back to the U.S. at the end of '98 and spent a couple of years as the lithography gate team leader for what was then TI's most advanced IC technology, I think 130 nanometers. But when TI was slowly but surely getting out of research in favor of simply very advanced, but just simply process development. And so I was lured under false pretenses to work at Zyvex Corp in 2001, where I was expecting to work as a contributing engineer/scientist, but I'm there for a couple of weeks when Jim Von Air, the founder of Zyvex, tricked me into joining his management team by offering to make me his CTO. And so I fell for it. Up until that point in time, I'd been largely just a lab rat.
So how many employees did Zyvex Corp have in 2001?
At that time, they had about 40, and we got up to around 50 over the next period of time. Then trimmed back a little bit, and then Jim had founded in 1997, but we developed a couple of significant business lines: carbon nanotube enhanced polymer composites and nanoprobing for the IC industry. And I forget how many people we had at that point in time, but we trifurcated the company into three parts: the CNT enhanced polymer composites, which became first Zyvex Performance Materials and then Zyvex Technologies. The nanoprobing stuff, mainly in the IC industry, went over to Zyvex Instruments, and the core working on what Jim was originally interested in having us work on, which we're now calling atomically precise manufacturing, became Zyvex Labs. I remained the VP of Zyvex Labs for a while, but after a few years, Jim decided to go ahead and make me the president. So I just got more management duties, which I fully embrace now. But it's I get an itch to get back into the lab, and every once in a while I'll sneak in. But I've hired a really great group of folks, and I just need to get out of their way and let them do their stuff.
That's how I feel about my students and postdoc. So talk a bit about the motivation Jim had for starting Zyvex back in 1997.
Well, so it's fair to say that he'd read Feynman and Drexler, and bought the whole what then we're calling molecular assembly model, hook, line, and sinker. And I should say that he'd made he used to work at TI as a software engineer, left TI about the same time I joined it, just a year before, I guess, and founded he decided there was money to be made in the software business. Turned out for him, that was absolutely correct. I built his company up over 11 years and sold it at exactly the right time to Macromedia, which made him a very high net worth individual. And instead of there's not that many people that end up in that situation, but the ones that do, the men anyway, tend to buy sports franchises or small Caribbean islands, or start amassing a fleet of yachts or sports cars, high-end sports cars or something. What he decided back in the mid-'90s, when nanotechnology was not a particularly popular buzzword, is what the world needed was a nanotechnology company. So he founded it in 97. I actually met him in 98 and was intrigued by what he was doing, but wasn't sure even he had enough money if he was going to work just explicitly on that project, which was his intention at that point in time. But he started hiring a bunch of really bright kids, mainly right out of college, and really, really smart individual decided that he needed to be a little more opportunistic and look at developing some technology along the way. He was doing some incredibly cool MEMS, especially MEMS assembly stuff, and had some other nice stuff going on. So, and again, TI was getting out of stuff, so I joined him. He tricks me into being into management and starts to work on, okay, what are we going to commercialize? And so the two things that really, I failed, frankly, to commercialize incredibly cool technology in the MEMS assembly area, but we did develop a very effective carbon nanotube functionalization technology and developed a really good nanoprobing technology, which is the dominant, what was Zyvex Instruments got acquired by DCG Systems in 2010. DCG got bought by FEI in 2015, and last year FEI got acquired by Thermo Fisher Scientific, and the division that used to be Zyvex Instruments really has a nice little micro dominance, not in the production line, but in failure analysis, and bringing part of bringing early ICs up with some fib circuit edit and so on. So they've been extremely successful along those lines. But so we've continued with, in 2007, Zyvex Labs has been concentrating mainly on atomically precise manufacturing. We got a really great DARPA program on the tip-based nanofab program that ran for almost 5 years, and picked up a nice ARO project to work on STM lithography for for supporting quantum computing device fabrication, and got a couple of years ago an atoms to product program out of DSO and DARPA.
Okay, so let's talk about those things. Talk then about what is digital atomic scale fabrication.
First, I want to make 5 major points, and then we can kind of talk about the details of those 5 major points.
Sounds great.
I first want to assert that the promise of nanotechnology is largely unfulfilled because of the lack of manufacturing precision at the nanoscale. We do have some very useful nanotech products in terms of improved materials, in terms of better sunscreens, but not the complex, reliable nanosystems that will be possible once we have the manufacturing precision required to make them. The second, and this is the most important point, I believe there's a spectacular opportunity to develop a technology that I'm calling digital atomic scale fabrication to provide the much better nanoscale manufacturing precision required to fulfill this promise of nanotechnology. And this, I believe, will enable very complex, extremely reliable, and really spectacular performance products that are not restricted to electronics. And I'll come back to this, it's not going to happen overnight. Third, I think the path to this technology I'm calling digital atomic scale fabrication that will have unprecedented manufacturing precision is a digital approach, a digital fabrication approach that uses the making and breaking of chemical bonds as its binary process. And it needs to have the ability to spatially, digitally address where the chemical bonds are made or broken. Otherwise, we're talking basically just chemistry. And very importantly, it will beg, borrow, and steal from the path that took our information technology from analog to digital. I think there's a great analogy to be made where nanotechnology is now compared to where our information technology back was before it went digital. And the most important lesson in this that we should expect to learn is error detection and correction. Just like in IT, there will be errors in transmission in a variety of places, but you can get essentially perfect digital results if you do error detection and correction. I'll come back to that. Fourth, the point is that it is not the semiconductor industry that will start this new revolution, and I'll probably come back to that point. Lastly, once digital atomic scale fabrication takes place, first with nanoscale products, where I think it has to start, the improved manufacturing precision that will come naturally as we go down this path will lead to atomic precision, where the error detection and correction will allow essentially perfect, physically perfect fabrication in spite of the inevitable processing errors. This will allow for what I'm calling an inverse Moore's law that will drive our technological progress, economics, and standard of living for the rest of this century. So those are the 5 major points I wanted to make.
Why don't we take the question of, is digital atomic scale fabrication chemistry first?
So first, I probably need to give my definition of what I mean by atomic scale fabrication. And let me start off by saying what I don't mean. Okay. It's not a fabrication process that is just controlled by digital computers, digital electronics. And it's not something that uses a design grid, which you can consider digital, but that's just the way you design your part. I'm looking for a fabrication process that takes advantage of the quantized nature of matter, the process itself. It takes advantage of not only the chemical aspects of atoms and molecules, but also of their wonderfully invariant spatial nature to control the size of what we're fabricating. To be a little more specific about that, I sort of said this, but I'm going to say it again. It's a process that as the binary result you're looking for. Digital, of course, can be multi-valued. I'm going to restrict my comments to binary results that makes or breaks chemical bonds. And not all chemical systems work beautifully this way, but there's certainly making or breaking chemical bonds can be very digital. Either you make the bond you want to make or you break the bond you want to break. It has to have a reasonably low error rate. If it's just really chaotic, it would be hard for the error detection and correction, which I'm going to claim is required to make it possible. But the thing that really separates it, so far what I've said could be chemistry, what really separates it from traditional chemistry is the ability to digitally, spatially address what specific chemical bonds or bonding sites that you're working on to either make or break these chemical bonds. And so probably at this point in time, and also we have to have some way, some processes that can do error detection and error correction. And that can fall into a wide variety of things. But I think at this point in time, I need to explain the basis for why I'm thinking all of this and the main technology we're working on. And it's this scanning tunneling microscope lithography that Joe Lighting and Faden Navorse developed back in the mid-90s. And it uses an STM, which normally can be operated in a mode where you're imaging things and you don't make or break any chemical bonds. But if you take, and there's other material systems that this would work on, but what's been developed is on a silicon 100 surface, the principal surface that you like to make integrated circuits on these days. You get a 2x1 reconstruction. You have to go through some surface prep, but then you can hydrogen passivate the surface where every surface silicon atom has a hydrogen atom. Now, without that hydrogen atom there, you've got a pretty reactive surface. You've got a bunch of hungry covalent bonds that are willing to attach to a large number of different things that might, molecules or atoms that come their way.
In the case of silicon, it's extremely hungry.
Yes, it is indeed. But if you take that, and you have to do all this in UHV, but if you do this UHV sample prep, and then you actually have to crack the hydrogen. Molecular hydrogen doesn't stick, but atomic hydrogen does. And if you do it right, you can get a beautiful 99% coverage of every surface silicon atom with a hydrogen atom in its place. By the way, this digital atomic scale fabrication process, I'm going to talk about in a inorganic setting, but I think a huge amount of it translates very nicely to organic and other chemistry settings. But let me come back to this thought of, think of the hydrogen atoms as protection groups that keep things from reacting with the silicon surface. Okay, with my STM, I can come I can get into a higher current or higher voltage regime, and normally, at least when you're imaging silicon surfaces, people like to tunnel electrons from the surface to the tip. We switch the bias and tunnel from the tip to the surface, and under the appropriate conditions, well separated from imaging conditions, we can remove hydrogen atoms from the surface, and we can do that with atomic precision. You can, if you want, target individual hydrogen atoms as Bob Walco does and pop off individual hydrogen atoms just exactly where you want to do so.
So the difference between chemistry and the kinds of atomically precise manufacturing you're talking about are, in the chemistry case, you might have this ensemble of particles or molecules that are constantly colliding with an active site on another molecule, and occasionally one will have the right orientation and cause the reaction. But it's honestly very rare that orientation would happen so that you get the reaction. In your case, you're talking about taking, in this case, an STM tip and doing chemistry specifically where you place the STM tip.
No, not exactly. Not exactly. Really, think of the hydrogen on the silicon surface as a resist. Now, it's not a physical resist. It does not resist a monolayer of hydrogen doesn't resist any etch process that I know of. But think of it as a chemical resist, where I'm modifying the chemical properties of the surface, or even think of it as Jim Tour makes spectacular use to make these very complex molecules of protection groups so we can add what other molecule or atom that he wants in a very specific place. But then he has to think up very clever and intricate chemical synthesis approach, which often takes multiple steps to remove just the protection group that he wants, then bring in the reactant that he wants to stick in that specific spot. Here, I'm looking for a much more industrial, straightforward approach. I remove hydrogen atoms where I want molecules or atoms to react. And then it's just chemistry, but it's surface chemistry, but I'm in control of where the reactions happen. And the tip doesn't have to be around. Our intention and what we've done regularly is we remove a pattern of hydrogen atoms. There's a certain length of time that we can spend doing that, even under very good UHV conditions. But if you do things right, you've got several hours before you get much of any contamination on the surface. So we do our patterning, then we bring in the particular precursor molecules that we want to stick where we've removed the hydrogen atoms. So we can control exactly where that happens. So it's not where the tip is. The tip is I'm just doing lithography. I'm making a pattern in my resist. Then I bring in, and just to give you some examples, we've done patterned atomic layer epitaxy, where we bring in disilane and we put the disilane molecules on a silicon surface where we want them, and it's a self-limiting process. So we come in and so we make one pattern, dose with disilane, come back and pattern again, dose with disilane, come back and pattern again. And there's a temperature regime in which the hydrogen is still stable on the surface, and you can get this epitaxial growth to happen selectively where you want it. Now, we haven't yet, there's a problem in that the disilane deposits, in addition to 2 hydrogen passivated silicon atoms, it dumps 4 other hydrogen atoms on the surface. So I at most get, with the current chemistry, a third of a monolayer of silicon atoms down. So it's a pretty inefficient process. We have to pattern dose, pattern dose, pattern dose. Then I've put enough silicon atoms down on the surface to make a monolayer. But even then, I don't get a monolayer. I get 2/3 of a monolayer and some island growth on top of that first monolayer. So it's not yet to where I can do really atomically precise manufacturing, where every atom, I'm in control of where every atom goes. On the other hand, there's a lot of other processes that look very exciting, like putting dopant atoms where you want. You do your lithography patterning once. You expose, right now the technology that works very well is exposing to phosphine. The phosphorus atoms stick where the hydrogen's not. You do a little incorporation anneal. The phosphorus atom goes into the silicon lattice, kicks out a silicon atom. Then you do low temperature MBE overgrowth, and you can essentially make whatever pattern that's atomically precise of dopant atoms and all the atoms, if you do this right, stay on a single silicon 100 plane, or at least the vast majority of them, and you can make some remarkable devices, we believe, that way.
Let's say we get really good at this approach. What does it enable that we struggle to do today?
Okay, well, the most exciting or the most notable result that I can point to is really the work of Michelle Simmons, who took the Kane qubit, Bruce Kane, an American working in Australia, doing a sabbatical there, I think, came up with this idea that you could use the very long-lived nuclear spin of phosphorus in a silicon lattice as a qubit. And so Michelle, an English woman who immigrated to Australia, picked up the challenge of trying to figure out how to make this Kane qubit. He was originally talking about using surface gates to control the interaction and setting the spins. She realized that by doing a little bit more patterning, other than putting a single phosphorus atom, she could make electrical leads for gates that could set the spin and control the interaction between qubits. So quantum computing, although there's a lot of other potential ways of getting there, that is the most scalable, and they have outrageously long-lived nuclear spins, very, very long decoherence times. It looks like a spectacular way. Certainly there's a lot of competition there, but that's one way to make quantum computing. Something I was going to maybe hold off and mention until later, but I'll mention now, using very similar technology, we think that we can make designed 2D materials by making patterns of dopant atoms in a single silicon 100 plane and create the band structure electronic band structure that we want. And that could be useful technologically, but it's also very interesting to a bunch of physicists that want to do things like Hubbard model experiments, potentially look at topological insulators. And we actually have a workshop that we're organizing with people from Sandia National Labs and also NIST that we held January 23rd and 24th at NIST in Gaithersburg. And we've got a pretty interesting group of invited speakers, a lot of them from other experimental areas, some cold atom guys, some trapped ion guys, some quantum dot guys that will present, guys and gals that will present their approach to doing some of these physics experiments to explore quantum interactions, but then compare and contrast to this relatively new approach that we're suggesting. So that's an exciting way of getting into a new regime of solid-state physics experiments. The isotopically pure silicon has been called a solid-state vacuum, and we think it has some real interesting possibilities that where you can. Well, it's got its pluses and minuses with some of these other approaches, and we hope to explore that and convince one particular DARPA program manager, based on the information that we generate, that it would be worthwhile funding an effort to develop that fabrication technology and do those sort of experiments.
So I'm familiar with isotopically pure silicon in this attempt to reclassify, I guess it's the kilogram?
Yeah, the Avogadro project, yeah.
So I guess I missed a little bit about what you're thinking.
When you go to isotopically pure silicon, you get rid of the silicon-29, which has an unpaired nuclear spin. And so if you're worried about things like decoherence time in qubits, you get way longer decoherence time because you don't have these unpaired nuclear spins. It also turns out just optically that they can look at fine structure optically in the silicon that they never saw before in natural silicon. Actually the thermal conductivity goes up by about 30%. Intel gave a serious look to going to isotopically purified silicon just in their standard wafers, just for the 30% increase in thermal conductivity. They didn't pull that trigger, but that's certainly an area of interest for a number of different things. It's of interest in a number of different places, but if you want to do some very careful physics experiments, well, I'll give you another example where this is maybe exciting. There's a guy in Florida, I'll try to remember his name, who's got DARPA money to make a solid-state atomic clock using isotopically pure silicon and using an isolated phosphorus atom. And it won't be as good as some of the other UHV approaches, but it stands a chance of being, in the long run, fairly cheap and extremely accurate atomic clock that can be made at millimeter cube size. So the isotopically pure silicon is a really interesting area, and it would be used in our particular case just to get better experimental results. This would all be most of this stuff is stuff we're talking about done in dilution refrigerators, magnetotransport if required. I mean, there's a wide variety of interesting physics experiments that can be done there. But that's all made possible because of this hydrogen depassivation lithography, which can put the current technology, there's one lattice spacing uncertainty in where the phosphorus ends up. We've got some ideas that I won't be able to talk about trying to tighten that up to where maybe there's no uncertainty and we can put the phosphorus atom in exactly the lattice site that we want it.
Let's talk a little bit about moving beyond a single tip, because I think a lot of people are probably thinking, you have one tip, how many things can you really position?
This is a great question, and I've been a litho nerd virtually my entire career, and so I have watched, and it's ongoing today, but the hundreds of millions, if not billions of dollars that have now been put into trying to take e-beam lithography parallel. But by the way, let me say that our STM lithography is just another version of e-beam lithography. I've got a cold field emitter that's delivering a very small set of a very small spot of electrons down on the surface that exposes a resist. It's the limit of a thin self-developing resist, a monolayer of hydrogen. We scan the beam around on the surface. We expose our but what's different, it's a digital process. But to back up, a lot of effort's been gone into making either parallel printing through mask or shape beam lithography, or a bunch of parallel e-beam approach, and a huge amount of time and money has been spent on that without much commercial. There's a few parallel beam machines out there, but it's a fundamentally very hard problem, especially to scale, because what you want is high current electron beams squeezed in really close together, and you get this Coulombic interaction that makes it more and more difficult to control the beams as you squeeze, as you get more current and more tightly spaced beams, and that's what you need for high throughput. And the difference is, in our approach, the beam path is ridiculously short, a few nanometers. It's low energy, it's very high current density, but the closest I can hope to get beams together, and let me back up and say the way that we want to go there is an array of MEMS nanopositioners, XYZ nanopositioners, that we think can be put on with relatively near-term technology, especially if you do your MEMS in a CMOS foundry, which you can do. You can put them maybe on a 200 micron pitch, and then you're at 200 microns distance, a few nanometers of low voltage, low energy electron beams, they just don't interact. So the beam interaction is gone. Okay, but what about the integration of all these tips? Well, if you do smart MEMS, if you build in a little local electronics to close the loop on the nano positioning, and you put in a little microcontroller, then all you need to do to build up an array is give yourself a power grid and a data bus. And you send out specific addressed patterning information to a little smart MEMS that makes the particular pattern you've asked it to where it's at, aligning to the silicon lattice. And when it's done, maybe it does a little error inspection. When it's done, it tells you it's done. So if you tried to have external computation and send in analog lines to control the MEMS, once you get built up to a big array, you'd have a really tough problem with crosstalk and immense wiring problems. You put everything on, like I say, a power bus and a digital address bus, then I'm not saying it's trivial, and there's still some significant, because I come back to our earlier discussion, tip reliability issues that have to be solved, but it's a linear, I believe in the number of tips, it's a linear problem, not an exponential problem, and to scale up to a very large number of tips. And at a 200 micron pitch, you could put 1 million tips operating on a 300 millimeter wafer. I do not think that's out of the question.
And just so make sure I'm on the same page, and I'll put a link in the show notes, this sounds a lot like, I believe IBM did this years ago.
The millipede, yeah. But you have to realize it was a parallel tip approach, but the tips only actuated in the Z direction, okay? And for doing what I want to do, there's potentially a way of having actuation just in the Z direction, but I'm much bigger fan of that will force you into a raster, in e-beam lithography terms, that forces you into a raster scan approach. And all the e-beam technology started off raster scan and went to vector scan. And so I'd much rather have you have much greater efficiency, and you can align actively to the silicon lattice, which you really need to do this kind of lithography the way we want to do it. You need X, Y, and Z positioning. So this is it is a parallel tip approach, but you'll need global positioning to move the tips around, because the area they're going to scan over is going to be a very small fraction of the footprint of the MEMS scanner. But the tips can operate independently in parallel, writing out the particular patterns that they've been assigned. So it's now a guy that I've got working on MEMS nano positioners. Well, he's working on the control loop for STMs. A guy named Reza Mohimani at UT Dallas. Again, a really superb control systems guy that has great nano positioning credentials. He worked on the control system for the millipede. back in the day. So again, non-trivial engineering, but everything that I'm suggesting here, I believe, is firmly in the technological realm. I do want to make a point. I want to come back to this idea of error detection and correction.
Let's do that for sure. And I think when I think what's the next step beyond, let's say, wafer scale, and I think, well, okay, if I want to do atomically precise manufacturing at a centimeter cube scale, or larger, meter cube scale, how do I think about that? And I think you're getting to this question of errors that might be introduced in this process and how I overcome those errors.
Well, so again, I've been trying to sell this story of digital fabrication for the better part of a decade, to be honest, because it's really appealed to me. But everybody, including Eric Drexler, told me, this is an analogy only an electrical engineer would appreciate. But the world has progressed since I first started telling this. Either thinking has progressed, or I've gotten better at explaining it. I go back and I look at the information age, okay? And again, back before it went digital and was analog information, we had television, we had telephone, we had radio, we had movies, we had records, we had tapes, and significant impact on our information technology. But it really didn't take off dramatically until we went digital. And it's worthwhile asking yourself, well, how come digital made all this humongous advantages? And the answer is there's a whole set of, Claude Shannon pointed out that there's huge advantages by going digital. You can have essentially immunity to noise. You can engineer in security issue. You can engineer in encryption. There's a great scaling that takes place here. But it's interesting that Shannon and von Neumann and Turing all talked about and demonstrated to some extent what you could do with digital computation. But it was Claude Shannon's roommate, or office mate, I should say, at Bell Labs, a guy named Richard Hamming, that tried to do more complex. They were doing simple things as demonstrations. He tried to do more complex computation. They always had errors using the best digital electronics he had available to him at the time. Realized that, wait a minute, at digital, I ought to be able to check for errors. Introduced Hamming codes, which has led to a whole host of error detection and correction schemes that are used that put up with, in some cases, a large number of errors, and yet in the end, the first order produce perfect digital results that have enabled this immense digital communication system worldwide that we have now, that's outrageously complex and yet at the same time outrageously reliable. So I think there's an analogy at the physical scale where we're given quantized size already, and we're given a lot of other quantization that's possible. So I think there's some, for instance, our hydrogen depassivation lithography is an outrageously, if we treat it this way, digital process. We have a digital address grid, the silicon lattice. The resist response is absolutely binary. Either you pop that hydrogen atom off or you don't. There's no partial exposure of the resist, which is a bane to conventional e-beam lithography. And we can inspect before and after the patterning that we want to do. And while we don't have we can go back and remove hydrogen atoms we've missed. Recently, both Bob Walco and a group at IBM Zurich have shown that you can put individual hydrogen atoms back down on a specific dangling bond if you want. So you can do error detection and correction. But let's take it beyond that. Well, let's think about digital information technology that wants to communicate over a noisy channel. Okay, what do? Well, we send a data packet of a certain number of bits, and we follow it up with some parity bits. And the parity bits are a lossy compression that has some relationship to the data packet. And at the other end, where we don't know what the information is supposed to say, we run the same algorithm that generated the parity bits on the data we received. And if we can reproduce the parity bits and we have a pretty good idea about the error rate that things are happening, then it's good and we take it. If it's bad, well, we just throw it away. Well, let's say I'm building a little nanoscale widget that where ideally I'm putting all the atoms where I want them, but I've made a widget. It's three-dimensional. I don't have access. Even if I did have access while I'm making it, it'd be very expensive to look at every single chemical reaction in every single place. Let's just say I've got an error rate that's low enough. I build something up. Already in this nanoscale widget, it's got inherently compressed information about its structure, its mass, its mechanical resonances, its optical resonances, its length, its width, its height. We can make these things, check them, and if they're out of whack and they're nanoscale, hell, we just throw them away. So there's, I think, a whole host of other, and I could go into that, but I think I've given you a couple of examples here where we can put up with the inevitable. Drexler and a bunch of other people have talked about making nanoscale things. They're beautiful, they're wonderful, but they're not taking into account, they're assuming in all their descriptions, they're assuming perfect fabrication. They may talk a little bit about some inspection here and there, but I think if they go very digital with the fabrication, that you can deal with errors in a much more reasonable fashion. And then, well, one other example. If you make your nanoscale widget and you've inspected it, you've decided, okay, and you've gotten to the point where it's essentially atomically precise, some little brick that's a certain number of lattice spacings in length, then you can do addition, where you bring surfaces together in UHV and they bond together. You can do addition, add these things together, these little bricks together, which may or may not need to be the same size, depends on what you're trying to build, and there's no error accumulation. So you can take things to start off with at the nanoscale, use hierarchical assembly, and build up and get atomic scale precision at much larger size scales through assembly if you start off with digitally defined, atomically defined parts.
Yeah, and I really agree with you in terms of error correction. And I think even in the examples that are generally held up as nature's atomically precise manufacturing, that what the cell does in terms of DNA replication and protein manufacture, right? There's other proteins in the cell that are looking for incorrectly made proteins.
Absolutely. I'm glad you brought that up because, and that's again back to, I'm talking about this digital atomic scale fabrication in one particular regime. I think it's applicable to a lot of other regimes. I've got some friends that used to do semiconductor processing that have run off onto the wet side and are doing DNA structures. But most of them are still not taking advantage of what nature does. Nature's got all sorts of error detection and correction mechanisms built in. And so, you're absolutely right. The biology of life only works with error detection and correction. And so I'm just trying to, you know who I mean when I say Ned Seaman?
Yeah.
He's one of the early guys that did DNA structures, physical structures. He had a great quote. Somebody referred to him doing biomimicry, and his quote was, "Oh, I wish I was so good to be a biomimic. I just think of myself as a biokleptic."
Yeah. I think there's chemical engineering terms. We call it separations. In bolt manufacturing, they call it sorting. In tomato growing and selling, they probably call it sorting. Every industry has its way of getting rid of what's improper, right?
Right.
And you don't have to search on YouTube for all that long to find some fascinating examples of different sorting techniques used in different industries.
Yep. So in a very large sense, this is a sorting technique. But if you take it to the digital regime and treat it as if it's digital, I believe there's some really significant advantages to be had beyond just inspection and sorting. Okay.
So can you talk about some of those?
Well, again, let me come back to the example I gave just a second ago, and that is if you can make things that are, if you've controlled your process well enough to make things that are a known number of atoms in some length and present surfaces that can be you can bring together and will do the chemical bond that you want, then one of the things you get in a digital process is you can do reproduction without error. You can do replication without error. So here, by adding stuff up, you've got no error accumulation as you build up. And precision, manufacturing precision. If I say Norio Taniguchi, I'm assuming you probably know who I mean.
That one I don't.
Okay, so Taniguchi is actually the Japanese industrialist that coined the term nanotechnology. He was working in the semiconductor business back then. And back in the 70s, he started paying very serious attention to manufacturing precision. And if you take Moore's law, more than anything else, it's about improving manufacturing precision so you can shrink your transistors and put more of them on a chip. And so he started plotting manufacturing precision starting at the beginning of the 19th century, and he plotted it in several different regimes, in sort of standard manufacturing and precision manufacturing, and then the bleeding edge of ultra-precision manufacturing. And if I just look at the subset of that data, would you care to hazard a guess of by what factor in the last 100 years manufacturing precision has improved?
Last 100 years? Factor of, let's go with 1 billion.
Oh, it's not nearly that good, at least in linear. It's about 100,000 times in terms of the linear ability to control something. If you took it volumetrically, it'd certainly be in the billions. But in terms of control, a critical dimension, one dimension that you're trying to control, it's been about a factor of 100,000 times. But if you look at his chart, he predicted beyond where he kind of extrapolated pretty accurately, a little bit conservatively, and it predicts today we ought to be doing things, we ought to be able to have control of manufacturing precision down sub-nanometer scale. And in fact, in terms of thin film deposition, we are there. Now, it hasn't expanded to a much larger, but if you think about that, and I will argue that manufacturing precision is one of the real both drivers and limiters to human technological progress. There's a bunch of examples of things that were thought up and prototyped hundreds, if not thousands of years before because they were prototyped but didn't make a big social or economic impact because there wasn't the manufacturing precision around to mass produce enough of them to make any difference. The wheel, ball bearings, steam engines, computing, some sort of computing machines, all had at least 100, if not 1,000 years in between prototypes, conception and prototypes, and widespread use where they had major economic impact. So if you take that and think, geez, we've had this tremendous technological progress over the last 100 years, and you ask yourself, is there another factor of like 5 orders of magnitude improvement in manufacturing precision to be had? The answer is no, there's not. We're running into the quantized nature of matter. And this is what's led pretty directly to the pretty much the end of Moore's law. I mean, there people keep grinding away on it, trying to get more and more transistors on a chip. But the beautiful linear then squared to area downscaling that's happened is pretty much done. So where are we going to go? I'm going to propose that there is an inverse Moore's law. Now, first of all, Moore's law, I'm going to argue, really is the product size started off small, got a little bigger for a while. For the last 2 decades, the chip size has been static. We haven't produced the device any bigger. And the chip function has been static. It's gotten a lot higher performance, but it's been static. So we're making digital electronics, and we're making them on chips that are, on average, a square centimeter. An inverse Moore's law would not improve manufacturing precision, but achieve absolute precision, atomic precision, start off making useful little widgets at the nanoscale, and let's say DNA sequencing nanopores. This is a great example of where insufficient manufacturing precision. People have been working on nanopores for a better part of a decade. It's got a great promise of as a way to do DNA sequencing. You can do very long strands of DNA. It can be very fast. And people know how to make about the size opening they need to make around 2 or 3 nanometers, but they can't make it precisely enough to control the translocation of the DNA up through the pore to have a decent readout mechanism. If we can make things with atomic precision and really control the size and the shape in 3 dimensions of those pores, and by the way, integrate some electrodes, then boy, that's going to be a high valued product, but we only have to make it to nanoscale. So that's successful. More money comes into the industry. We improve our manufacturing precision and don't scale up. We not scale down. We've achieved absolute precision. Maintain that absolute precision and scale up to reach a much larger range of products. They don't have to be just electronics. And as the volume that we can efficiently manufacture, the volume in terms of physical size of any one useful product grows, then we have this beautiful exponential trend again of upscaling instead of downscaling. So instead of downscaling and static size of the product, we're going to scale up, achieve manufacturing precision where we can't make it any better. Now, of course, we can expand it to different materials and be more efficient with it, but we achieve that manufacturing precision at absolute and then scale up. That's why I think of it as an inverse Moore's law.
So when we scale up and go this other direction, and thinking back to our brief discussion about error correction, one of the challenges will be to figure out when and where to do error correction, at what length scales. Because you can imagine putting atoms together and building up a structure. You get to some point, and another atom, it doesn't change the size of the structure. And so what you need to do is take nanoscale structures and combine them to microscale. And you're going to have separations or some kind of error correction along the way, no?
Yes, I completely agree. The big advantage is that if you've done your error correction to start off with, then your ability to combine these things through assembly gets a lot easier. But you're right. There will have to be are you familiar with this DSO program that we're a part of that's called Atoms to Product?
I do know it.
Okay, so John Main, I think, beautifully argued that, that there's certain size scales that assembly is going to be effective. You can grow up maybe 3 orders of magnitude. Beyond then, you're going to have to go to a different technology to assemble things. You can take that digital approach into assembling things without error accumulation and dramatically improve your chances of maintaining that precision and build up very, very superior products because of that precision that you can extend to larger size scales. There's one other point I kind of want to make that maybe will make a point that I want to make here, and that is virtually all of our current nanofabrication technologies are analog in nature in that they treat atom material as if it's infinitely divisible. That goes for all our current litho tools, deposition, etching, CMP, you have it. They all pretty much, there's a few counterexamples. Atomic layer deposition is one that at least takes advantage of the quantized size of atoms and molecules to control size. So let me do a simple little thought experiment. Let's say we're doing thin film deposition and we want to control that thin film thickness as carefully as we possibly can. Let's take physical vapor deposition, evaporation, sputtering, what have you. The first thing you have to do, you got a surface you want to coat. You have to make sure you have got really uniform flux of your atoms or molecules that are coming toward the surface. You got to have really good flux monitors to measure that. So you got to do really good metrology to make sure your flux monitors are telling you something that's relevant to what's landing on your sample. Then if you've got any topography whatsoever, it becomes much, much more difficult if you're not going on a flat surface. So let's switch over to, let's think about atomic layer deposition. Well, after you ignore the little bit of an induction period where the growth isn't really uniform per cycle, there's a few cycles you have to get past, the amount of material, the thickness of the material that you put down per ALD, self-limiting CVD process is outrageously controlled. And you don't have to control the flux very well at all. So you can overdose, and because it's self-limiting, you're in good shape. So you just turn the ALD crank in integer number of times, and you've got a much better control, much easier to control the thickness there. And by the way, it's very conformal. So if you've got topography, then you can maintain that precision on the topography. I'm not saying that ALD is always universally a better way to deposit thin films. I am saying that if you treat it digitally, it's a much easier path to really, really precise control of the thin film thickness.
Okay, so in the interest of time, I think we need to wrap up. We could have another conversation on this in 6 months and talk about entirely different things.
I hope so. Let me make one more point real quick, or ask me, why won't semiconductor manufacturers do this?
So I got a good question. Why won't semiconductor manufacturers do this atomically precise manufacturing?
That is such an excellent question, and the reason is twofold. One of which, and you would normally think that they might be the ideal industry because they've really pushed manufacturing precision in a very dramatic way. But it's highly tuned and specialized to doing digital electronics, okay? And because they're doing digital electronics, they're willing to put up with actually what would normally be considered horrible relative precision. Okay, trust me, a really, really good semiconductor lithography process gets you at best plus or minus 5% of CD control. And it's actually worse than that, what they're doing now. And have you done any carpentry?
No, not personally.
Okay. Part of my misspent youth was in Houston, Texas, doing a housing boom. And so I was on a framing crew that built houses and apartments very quickly and not very well. Imagine I'm up on the roof and I measure out a rafter and I call down to my buddy Zeke, cut me a rafter 10 feet long. And he sends me up a rafter that's 10 feet plus or minus 6 inches. It's not going to make a great house. Okay, try to think about designing an internal combustion engine when you got to put up with plus or minus 5% relative precision. Okay, so this is what the semiconductor industry is really used to doing, so they're fine with sloppy stuff. The other reason is that they're so huge now, they're not going to be interested in the niche markets that are where atomically precise or really, really precise manufacturing is going to be required. They just won't be interested.
This is a la the inventor's dilemma.
Exactly. One of the last things I want to do is make a plea. First of all, if you can list, I will send you some information. If you could list stuff on this design 2D material workshop that'll be at NIST in January, I'd appreciate it. The other thing is that I took a course last year run by the Small Business Administration called Emerging Leadership or Emerging Leaders Program, and it's really for people running small companies. And they convinced me that that Zyvex Labs should blog. And you had a really interesting discussion on one of the podcasts that I remember, a guy at Rice that blogs. So we've been blogging for a while, but nobody's paying attention. So I would also like to, and we've got some interesting things in there. I'll throw out one little tidbit. I'll end up blogging more about this very topic, but I made an attempt to attract people. I gave a talk around this, and a graduate student at UT Austin sent me something that I was not aware of. It's a line. It's a paragraph out of Arthur C. Clarke's 2001: A Space Odyssey, out of the novel, not out of the movie. And there's a relatively glaring arithmetic mistake in there, and it has survived a huge number of comments about, and it's about the exact 1 to 4 to 9 proportions that in the novel that he talks about that the obelisk has. And there's a simple arithmetic mistake in there that people have missed while still arguing about the 1 to 4 to 9 ratios. And there's years of arguing about whether in the book it says, well, it's the square. The 1 to 4 to 9 is the square of the first three integers. And there's this huge argument about whether 1 is a prime number or not when the prime number never comes up. And so I was amazed to find it, and I've looked in every edition of the book that I can find, very early ones, very late ones, hadn't been corrected, and nobody's noticed this. So there's an interesting discussion about that, and other useful things. So if we could get some of your listeners to go to our blog, it would make me happy.
Yes, we'll put links both to the DIST workshop and to the blog, and I will go look at the blog, so you at least have one person.
Oh, that'll be good. So that will encourage us to blog more frequently. I think the last thing we put up was in July, and we definitely need to do it more frequently than that. So I'm going to start mentioning this. Well, let me say, Michael, I have enjoyed this immensely. Like I say, I'm a fan. I've listened to a number of your podcasts already, not all of them. I'll go back and hit some more of them. And thank you for this opportunity to talk about what I think is a really important concept that I think has a great future, and I think really will be the path that enables first just better nanotechnology applications at the small scale, and later I really think can lead to a new manufacturing paradigm where we do the wonderful things that happened when we took our information technology from analog to digital, that if we can take our manufacturing technology from analog to digital, that'll have huge advantages.
Well, I think you ended that beautifully. So, John Randall from Zyvex Labs, thanks so much. We'll have to do it again sometime.
I'd be happy to do that whenever you want me back. Thank you, Michael.
You've been listening to Nanovation. If you enjoyed the show, please leave a rating or write a review on Apple Podcasts. Show notes are available at fillerlab.com/nanovation. Nanovation is recorded in the Marcus Nanotechnology Building on the campus of Georgia Tech. Andrew Cannon edits the show. I'm Mike Filler. See you next time.